Good afternoon, everybody. This is our Sunday Space Show afternoon program, West Coast time of the United States. Thank you very much for tuning in. Two great guests today, one from Germany, one from Australia. Uh, I'll get to them in just a minute. In terms of the upcoming schedule, there is no program on Tuesday. I'm using this time to try to get caught up in my archiving since I'm so far behind. Um, Hotel Mars is whatever John Batchelor has for us. And he has been getting his programs up on Substack pretty quickly. So what I've been doing is archiving his Substack page, which gives you video and the audio. So you can get the audio on the Spatial website. Substack has both. He is posting on YouTube, and I don't know where else, but I just take his entire archive and post it in our summary section. So if you want to pick it up on YouTube or another format, it'll be listed there by John. It's his show. It's not my show. I'm a guest host, and I appreciate that very much. But I figured to save time for me and to make life easier, I can put both audio and video up if I just use John's archiving process. So that is what I'm doing right now. Friday, our friend and Space Show Advisory Board member Amir Notia are bringing Moonshot Space to us from Israel with Shar Bahira and Fred Simon, and they are working on electric launch. And I believe they also have government money behind them, but that can be clarified because I think they might see a military or a defense perspective with electronic launch. So that is our Friday show. And then we are doing open lines on Sunday for two reasons. One is I threw it out to Phil on the last show that our president is put out a military executive order to cancel electronic launch on our latest Ford class aircraft carriers. He says they're too expensive, they're problem oriented, they break down, and he wants to pull them all into the shipyards and convert them back to steam, which will cost billions of dollars and disable a frontline carrier for who knows how long it might take to make that remodel. And Phil is always talking about electronic launch, the moon, all of this. So I challenged him to really look into this and what's wrong with electronic launch as a catapult on an aircraft carrier. Because maybe there's a parallel there. I don't know, but that seems really weird. We would spend billions of dollars and take a frontline warship offline that we need to put a steam catapult back in. And Phil is joining us right now. And then Joe posted really some interesting comments about All In Podcast and the cost of doing certain businesses and data centers and electronics in space. And I thought that was a pretty good short discussion from Joe, and Amir sounded off on that too. But those of you who listen to All In's podcast, that's a pretty interesting show. And if you don't know how to do it, they're on YouTube. You can actually watch the besties, or you can listen to it on any podcast server. Just go All In podcast, three words. Uh, so we're doing open lines on Sunday. So that's what we have coming up for today. And listeners, the company for today is one word, SpaceComputer. They're in Australia. And we have with us their CEO, who is in Germany, Filip Rezabek, and he's a co-founder, and their other co-founder, who is in New South Wales, part of Australia, Daniel Barr. And they are with us. They have different specialties. Their bios are on the website, so you don't need to have me read them on the Spatial website, that is, but do check them out. And they're working with NASA with a product of theirs called SpaceFabric, which is an orbital computing architecture which I'm reading, which generates all cryptographic keys after the satellite reaches orbit and performs mutual attestation across two independent secure statements. And apparently, as I understand it, NASA is working with them to develop and build a secure internet, which I would like to have for my own internet, because with Cox cable, it's hardly secure. But Daniel and Philip, welcome to the Space Show. One of you introduce us to your company. Did you guys know each other from Australia and meet in school? How did you get together to do this? And it's good to have you both on board.
Cool. Thank you for welcoming us. Maybe just a few clarifications. The reference for the space internet from NASA, I think that it got some lost in translation there. We don't actually work with NASA at the moment. It was a reference that probably came in the show related to the fact that we're building space internet infrastructure, and it's something that NASA has been trying to build for the past 30 years. And we can go into some of the details of that journey that we took some inspiration from. But this is still a novel and like a novel going thing. We haven't yet started working with NASA at this stage. So just to clarify there, um, and uh, and yeah, happy to jump quickly into introducing ourselves, our background stories, as well as a SpaceComputer, and we can get into the weeds and details shortly. So I guess for myself, Daniel, I'm based in Australia, CEO and co-founder of SpaceComputer, and we're building essentially a very secure kind of hardware, as well as software and protocols that are enabled by this hardware. We'll go into it shortly. Um, Philip here, based in Germany. Maybe you can give the brief introduction, Philip.
Definitely. So also, hello from my side. Happy to be here. Filip, the CTO and co-founder of SpaceComputer. And I'm also currently in my last phase of the PhD, focusing on the area of distributed computing, and especially focusing on the aspects of security, which is something that has been very close to me for the past over a decade, pretty much by now. And originally, I'm from Czech Republic, but I've been living in Germany, close to Munich, for the past roughly 8 years. And yeah, we met with Daniel several years ago and are together now building what we call SpaceComputer and providing a secure infrastructure for the space internet. I guess, Daniel, you can dive into more details. What does it mean?
What?
Sure.
Tell us about SpaceComputer. What did you have in mind when you both started the company?
Cool. Yeah, so I guess the journey started with the fact that we were both involved in the industry that is dealing with distributed computing and secure cryptographic system, also known as blockchain. And a few years ago, when we started getting exposed to interesting problems in the space domain, we realized that the entire stack of building interconnectivity in a secure manner for space systems, all the way from ground station through orbit, and then ultimately being able to interoperate between constellation, which is something that is currently like not yet vastly developed. All this domain is still underdeveloped essentially. And after getting exposed to some of those challenging problems from architecture and design point of view, we realized, okay, there are opportunities both in cybersecurity, distributed systems, and ultimately with the push of AI demand, there's more and more demand for data centers to migrate to orbit. And for data centers to operate securely, we need to be able to unlock efficiency from every spacecraft launched, and also be able to have shared tenancy or multi-tenancy, as it's sometimes called in data centers in general, such that every instance that is operating aboard the space-based data centers would know that it has proper segregation for the workload. The software is isolated and does not end up either being tampered with a malicious other payload partner or the operator. And this is a modality of operation that currently does not yet exist in how space missions are developed and operated. So ultimately, we basically saw that there is a domain with a lot of opportunities, and we started thinking through first principles, what needs to be designed for this to happen. And we came from a very different approach to how typically things are done in space, that we bring quite a lot of the open source ethos where things can be audited and software can be reviewed, peer reviewed. Everything that we do, we're ultimately interested in publishing in journals, working with academics, and getting very thorough review for anything, rather than keeping it closed source. So, long story short, in the past year and something, or it's already 2 years since we started, but the past year was very heavy on the R&D engineering implementation towards already finally having our version 1 of SpaceFabric hardware integrated aboard a satellite, which we maybe can mention some details, and some are still under embargo before there's the last clearance for this flight to happen in October. But we basically banded together with a group of researchers from different parts of the world and engineers from different parts of the world that each bring very unique expertise in order to architect, what we call SpaceFabric as the trust fabric for the space internet. And we can go into the details of exactly what are the components of SpaceFabric shortly. But I guess maybe just to give you some background of the team that we put together as well. Has been with us from the beginning, Professor Dalia Malki from UC Santa Barbara. She's a pioneer of consensus protocols and one of the key implementers of, at the time, two-party computation, which later turned into multi-party computation, so secure compute schema. And we also have with us Mr. Will Helsley, which was the VP of propulsion at SpaceX and has been there for 12 years since joining quite early. Been behind some of the key Falcon engine missions and everything. And yeah, we have in our team people from all over the world, because when we started the project, we were very much in the distributed systems security world, aka blockchain. And in this world, you have contributors and open source developers from everywhere, pretty much. So that kind of led us to build it as a global from day one company.
Are you launching on
Uh,
SpaceX rockets, or what? Who do you launch with?
Correct. As you know, the majority of things that go into space are going on SpaceX
On
missions,
SpaceX,
and
right?
yeah, there are some. We did discuss with the industry fellows that are currently working towards a mission with the Rocket Lab Electron, but this is it's kind of the outliers, I'd say. Like if we look at just the absolute quantity of things going into orbit.
So to the non-techies, we believe that there already is internet in space. So what do you mean by secure internet in space? What are you trying to do that is different from what exists today? And when I hear all of the talk about data centers in space, I don't, unless I'm missing it or I'm glossing over it because I don't understand it, I don't hear anyone talking about we need better internet or secure internet or something along those lines. I think if I had heard that and understood it, I would have probably spoken up and asked questions about it. But other people here know much more about data center efforts in space than I do. But it doesn't seem to be part of the discussion from my perspective, but I'm willing to be corrected on that.
For sure. So I'll let Philip shortly explain, but maybe just to give you the background and motivation there. When we think about internet in general, it's there's quite a lot of magic that happens in the background before you get fed this Zoom feed or website, right? You
Right.
have the actual fiber, or in my case, I'm connecting through Starlink, so already using some space infra.
Uh-huh.
You have routers, switches, you have um, different different protocols like TCP/IP. You have the servers, the data centers. You have like a full stack of technologies that enable this magic. And currently in space, we'll basically like share what's the current status and how we envision this stack playing out and where does SpaceComputer and SpaceFabric architecture plays a role. So I'll hand it over to Philip though.
So,
Yeah, so sorry, go ahead, David.
yeah, go ahead.
No, so to iterate on what Daniel was mentioning, so even though, of course, we don't want to really focus fully on the space data centers, but actually see already a lot of possible interest regarding the solutions we are providing. And with respect to where we gonna see the idea of space internet is that currently, if you look at it, as Daniel was mentioning, Starlink is more equivalent to the physical layer that we have as a part of the physical infrastructure on Earth with respect to the fiber. Because of course, currently everything is happening wirelessly or using optical links in space. But if you look at the typical internet communication, it's relying, for example, on the TCP/IP stack or is OSI, which is also having the additional layers on top of that help you with routing, managing, but also you have standardization and other support that in case one fiber communication, for example, go down, you have an option to switch to other providers that can easily go and tap into the ecosystem. Currently, when looking into the ways on how the space communication is structured, of course, you have a Starlink, you have Iridium, you have other networks, but it's hard to have a communication between this individual constellation. And even if you would have, it will be still more happening on the, let's say, RF optical layer, and also not as much on the protocols running on top of that. For example, like CubeSat satellite protocol and many others. And this is the part where we would like to provide a solution so that way you are not only relying on the physical capabilities that are currently provided by, for example, Starlink or other constellation, but you want to provide the software stack on top of that, which can be leveraging different capabilities that are coming from different constellations and different resources already in space. So this is just like a little where we would like to see it. And of course, since it's something that is quite novel with respect to how the communication and the interoperability between different constellations could be done, we also see the opportunity to see if we can improve on some of the challenges that we are currently seeing with the Earth internet and some of the challenges regarding scalability, security, verifiability, and see if there is something that we can unlock with respect to the unique properties of running such infrastructure in space.
So did you have you actually launched yet? Or I heard you say that maybe you're under embargo about this news, but in October, is that the first instance in space of this technology?
Correct. Correct. Yeah, this is the first instance of our technology.
Okay.
So we are very excited about it. We were working on the design for quite some time, and it's great to bring it from the design board, so to speak, into the first mission.
And so you've got a customer that's implementing this on their platform, or is it yours?
It's a mixture. So the details of how the mission itself will be structured is something that is still not possible to fully talk about, but there is also an interest, more not I would say customer in the sense of a paying customer. So we are covering the cost for the mission, but as a part of the verification and understanding that the technology can function and provide the capabilities that we are describing also, for example, in a SpaceFabric paper. This is definitely something that we want to build a POC about and use it as the next step for building up the capabilities of the infrastructure that we are currently targeting.
Just to clarify, this mission essentially is kind of getting us from no space heritage to space heritage, and on a very particular spacecraft that will have quite a few capabilities on it. So essentially, this will be our first platform to demonstrate multi-tenancy compute, for example, with more than one party. So essentially, that security piece that we were discussing earlier, where you are able to provide the trust guarantees for different workloads to operate aboard the satellites, rather than having it as a purpose-built silos, which is how often you see missions being built today.
Can you explain to me what then SpaceFabric actually consists of?
I'm happy to dive into it, but I see that also Marshall has his raised in the hand for a bit.
Well, usually I let David lead, but I was looking at what I did at Texas Instruments working on the C6X family of digital signal processors. Now, I would almost think that you would have in your communication protocols several digital signal processors, and then you'd have your core processors, and then NVIDIA would do the inference processing. So how many layers of communication is there between how many computers in your setup?
So with respect to how many layers, I think currently we are targeting roughly somewhere between 5 to 7 layers, similar to try to see what are the same as we see between the TCP IP stack and the SOC. So this is kind of similar parallel with respect to that. And what we see is like, especially there will be a lot of logic that has to be operating on the application layer, which I would say is the interesting part on that front. But of course, with respect to, for example, some of the future extension, we are very much interested in, for example, the routing capabilities, and see how some of the protocols and layers of these stacks can be adjusted to be more space native, so to speak, as well. So this is the part of the research efforts we are currently also looking into. For now, we haven't looked into it in such a level of detail because for now we don't have a large scale constellation and topology, but this is definitely something that we are interested in moving forward as well.
Mm-hmm. So you basically are making you have conceived way up here, and you're just doing the base right now, and hope to achieve the security levels you're looking for sometime in the future, like a year or two.
I would say maybe we're starting from the other part, so we hope that we will be providing the security guarantees provided by SpaceFabric. So I will dive into the details of what SpaceFabric is already on the first mission, but the aspect of, for example, multi-constellation, multi-communication will be something that will be unfolding in the future.
Yeah.
But kind of having the security assumptions already from day one, and we can kind of build and extend on top of that.
Yeah.
Maybe it's worth mentioning. It's worth mentioning that, as you might know, when you're working towards space missions, timelines can get quite long, especially when you're talking about government tenders and things that essentially are being you have like a lot of parties to coordinate, from which many of those are either big enterprises or government authorities. And then oftentimes what you see is that things are being designed for way into the future. And one of the dangers that you see is that you can end up building an obsolete system. So we're looking at it as something that is very modular, expandable, so that already from V1 of SpaceFabric, it will be extendable from there rather than having to be. Yeah, sorry, I see Bill has his hands up. Yeah.
Bill, you're muted. You're muted, Bill.
Sorry about that. Yeah, I'll let David ask his question since he was in line.
It was answered in the discussion with Marshall.
Okay, very good. Yeah. So you mentioned that you were going to be launching on someone else's platform. Can you share who that is?
We can't share yet who that is. There's some, we were supposed to, by the way, this is like anecdotal, but we were already having some, one of the common space media out there going to write about it this week, and we just have to put it on embargo because there's some last minute spacecraft clearance that is pending, and our partners basically requested that we keep it under veil for just a little bit longer. So it would probably be sometime around end of September that we'll announce more details on this mission. And then there's also like there's a few partners involved there, and each of them has a bit of sensitivity. So like we're kind of like waiting for this to unfold before we share the full details.
Sure. It's a cliffhanger at this point for us, right?
Do
Another question. You mentioned that some folks are using Electron as a launcher, and I'm curious, would that be an option for you? Are there, weight or other constraints that would prevent you from being able to use Electron as a launcher?
Maybe I can take that one and I try to unfold also the aspects of SpaceFabric with respect to where the architecture is heading. So as a part of the solution, we are focusing on building the payload, let's say the computer services on board of the spacecraft, which is mainly providing us the main compute that can be running on any type of rideshare options at satellite, self-standing CubeSats of satellite and try to provide a different type of modular design of the hardware that can be later on integrated already maybe into small sats, CubeSats, all the way into more powerful hardware, into more powerful satellites as well. So on that part, it's not really constrained to just like really aim for the massive data centers in space, but can be already integrated into current technologies. And the more important part is the hardware is providing the fundamental security assumptions with respect to, for example, having the root of trust that is coming from the hardware, but we also focus on building up the software stack on top of that. And kind of together with the hardware and the software stack, you are able to unlock some of the unique properties that we see, for example, multi-tenancy, so that we can actually have a hardware-enforced trust boundaries between different software stack running on the same compute. So for example, as we currently see on servers on Earth, if you are using virtual machines, they have some form of like a software enforced virtualization. But of course, it can also mean that in case one malicious party on one virtual machine breaks out, it can also compromise the other virtual machine running on the same physical hardware itself. There already is an existing technology that aims to make this much more challenging, called trusted execution environments. And this is something that is already being discussed in the context of confidential computing and secure computing on Earth. And what we are doing, we are bringing these concepts of this technology to space and try to make it, so to speak, space native. Because, of course, there are some additional challenges with respect to bringing stuff to space, for example, like radiation, heat dissemination. But there are also unique opportunities with space, which is especially the physical isolation. Because once you launch things to space, you are actually in a perfect location where you don't really have to worry about someone, at least as of now, going and physically tampering with your computer, because the satellites are flying in quite high speeds in the orbit. And unless the technology evolves in the future, when you can easily go and dock and physically tamper with your device, you actually have these unique properties of the physical isolation. And kind of combining this hardware and software stack, you can actually already extend your current missions in the future and make it more secure and more robust to not only, for example, have the trust assumptions enforced by contractual obligation, but have it enforced by the cryptographic means that are unique to the operations of the hardware and the software together on the respective payload. So we can provide our own compute resources, which is something that we also plan to do with the upcoming missions, but actually are also talking with other bus providers and satellite manufacturers if they would be interested to integrate some aspects of our hardware on board of their missions to unlock these unique features. So with that is basically the first component is the hardware, and the software is something that has several components to it. One part is robust and resilient and reproducible build for the operating system on board of the spacecraft as well. And then we have several protocols running on top of that, where the most crucial one is called Satellite Execution Assurance Protocol, which is a protocol that you can think of it as a challenge and response protocol between the ground segment and the space segment, where you want to be attesting that the computation itself is really happening in space. And the way on how we design this protocol is that I know over which orbit the satellite is flying, and I also can determine over which ground station the satellite will be flying. And at the point in time when the satellite is supposed to fly over this particular ground station, the ground station will issue a challenge that, hey, are you at this particular location? And if the satellite is able to answer within the respective time window, and the ground station is able to confirm that, okay, here's actually, it's really you, I got a correct message based on the cryptographic key material that has been generated in space, you basically collect an endorsement from one ground station, but we can assume you will be collecting the endorsements from multiple ground stations. And these are the two main components, the hardware, the software, and the satellite execution assurance protocol, which kind of bind the assumptions together, and we can unlock the new protocols that can be built on top of that and provide these unique properties. Where I would say the maybe most unique property we see is to get verifiability end-to-end, which is, I think, very crucial in the supply chain scenarios. So, for example, if you take an image in space, using the cryptographic means we are using under the hood, you can actually get a cryptographic attestation that, hey, this image of Earth is really coming from this particular spacecraft, and it's authentic and wasn't tampered with, and these guarantees can be transferred back to the user on Earth, where they can later on take decisions based on this, for example, imaging data. But of course, it can be translating to any type of other use cases as well.
So this is far from just a hardware implementation. This is a system level solution across a lot of different applications, and so it sounds like the software development has been an enormous piece of the product that you're selling. So I'm curious: are you more a software development company or a hardware development company? Or
it's a great question.
Resources split?
Yeah, I think that's a very great question. I would say currently we see ourselves more as a software development company, but we have, of course, our also hardware team that is working on the aspects of making the hardware space grade, so to speak, and helps us to design the PCBs, helps us with the shielding, the radiation. But I would say as a part of the main capabilities and the core strengths of the team, we are a software company. This is basically also the type of agility and know-how we try to bring to building up the infrastructure for the space internet as a kind of mixture of the hardware and the software, but mainly try to focus on the software capabilities.
Maybe I'll chime in here. It's an interesting question because when you're talking about hardware for space companies, it brings the question of what aspect of hardware are you building rockets? Are you building bus systems? Are you building other parts of spacecraft, right? So when we're thinking about what's our kind of secret sauce, if you wish, or core competency in the company, the software is what is enabled by the hardware that we're building. And the hardware, these are essentially embedded systems and the PCBs, and maybe now we're starting to look a little bit at the silicon level. But generally, it's not so much the spacecraft hardware and the rocketry and all that stuff. It's a lot more focused on the compute as the core competency. So the compute core, if you wish, right? So that's where there is a hardware element to it, but the hardware is essentially what enables the software outcome rather than the other way around. That like we're like would be a heavy lifting rocket company or other type of space company.
It might be helpful if like if you told the users a bit about the OSI model in networking, and then explain like what layers of the model you guys are focused on, or if you're even staying within the rules of the model, or if you're reinventing it in some way in space. Give some like the audience some idea of what that is. You're
Yeah, I
familiar with the
can chime
OSI
in.
model, right? Yeah.
Yeah, exactly. I can chime in. So the ISO model has 7 layers. So kind of starting at the layer 1, so to speak, is the physical layer, which is, I think, really providing you the physical wiring with respect to where we sit currently on the hardware level, which, of course, if we translate it to the space, right, it will be either RF or optical links that are really providing the end-to-end communication. Then we have the layer 2 afterwards, is operating on the data link layer, which is, I would say, just like agreeing that the individual parties are able to access the medium at the right point in time. This is, for example, where Ethernet has really become the dominant technology on the L2, where you can later on have the individual parties. Afterwards, you have the destination layer, which is the prominent protocol on this layer is the IP protocol, which is really basically handling and routing the traffic between the individual parties. Then on the 4th layer, you have the transport layer protocol, which is mainly providing the differentiation between the reliable protocol, the TCP protocol, or the UDP protocol, which are the most 2 prominent protocols on this layer. Afterwards, you have the 2 layers in between, the application layer and the transport layer, which is the session and presentation protocol, which currently I would say are a little bit blurry with respect to the features. It's somewhere between, let's say, agreeing on the sockets and other capabilities, agreeing on the format of the headers and the cookies, and so on and so forth. And then you have the application layer protocol, where I would say most of us are operating in regarding the HTTP traffic itself. If you cannot take this model and try to apply it to where the space currently sits, it's mainly operating, for example, on the level of Starlink. Of course, you have a different routing between Starlink satellites, but it's mainly operating on the first 2 layers, which is the aspect of the physical and the data link layer. And if you would like to consider maybe bridging it to the future, we would like to see if there can be something done also on the networking layer, which is the routing, for example, between different constellation, not only within one particular constellation itself. So this is, I would say, for us the future, but where we currently sit is mainly between the transport and the application layer. So you want to be providing the security assumptions coming from for the application layer protocols, but see how we can tailor some of the underlying protocols for the space native application, maybe like a modification of TCP, modification of UDP, and try to make it more fitting this particular context as well.
So yeah,
So
so
this is
you're,
just like
you're
hopefully for the context.
so I think you said, I mean, you sort of said both both link layer, transport layer, but then you sort of said you're focusing more on the upper layers of the software layers. So that's like 4 to 7, right? So that's your real focus.
Correct.
And yeah,
Exactly.
okay. Yeah.
Do you have a customer yet? Do you have funding, and where does it come from? And why would, as your literature say, NASA gave up on this 30 years ago? I'm sure the technology is very different today, but is that why it was given up on? The technology didn't exist, or was there another reason?
Yeah. So with regard to customers, pipeline, and partners, we cannot yet share these things in public at the moment. Um, it's I guess like maybe it was not the best reference to discuss the NASA internet, but essentially something that we noticed come up in many conversations we had with partners, like, oh, that's really interesting. NASA JPL was already starting to look at studies into interplanetary internet in the 90s, and it never took off. And then we started looking into what were the things that kind of happened since the 90s there. And there were a number of efforts. It's just that a lot of the assumptions in the early years were different to how things operated in the end, and space kind of took a privatization tangent ultimately, and you started seeing less of these things being developed under NASA for that matter. So originally, their objective was to enable communication for astronauts that are in different parts of space. Now, this will probably happen at some point, which would be awesome. I'm looking forward for it. But at the same time, what will happen far earlier and what needs to be ready now, and that's what we're kind of seeing both from government interest as well as commercial interest, is that AI is just such a mega sink for compute demand. And there's so much security that you're gonna need when you're deploying those models and different workloads that operate on edge devices. There's so many opportunities for attack surface increase. You see it already in geopolitical tensions that we're seeing today, where ground stations are being attacked. Social engineering for different people that work in different parts of the stack, whether it's the operator of different communication parts. Much of the security is currently done on Earth as software defined, and then oftentimes you don't have the same ability to do verification based on the hardware. Hypothetically, you could have, let's say, an image that is serving someone to make a critical decision for military or for supply chain finance. You have an image that is originating from a certain part in orbit that you don't have any ability to verify its integrity, that it actually originated from orbit and did not get some tampering before it got pushed into some key decision about military attack or some prices of oil or whatever it is. And these things are already relevant today. You see basically massive increase in cybersecurity, cyber warfare, essentially, that takes place. And this is before we even migrate most of AI compute into orbit, which is a big part of the trend. I'm sure that you guys are aware of the StarMind project from SpaceX that is aiming to launch 1 million satellites. There's our industry colleagues, Star Cloud guys that are the first people to launch the H100 to orbit, NVIDIA H100, and demonstrate some inference. Every player that understands that permissioning and issues with energy on Earth is going to be constraining the growth in AI, understand that we need to start building the AI compute stack in orbit. And for that, you have every kind of application incorporating AI into it, and for that you need much greater degree of security. And the space native TEE that Filip mentioned earlier, it's one aspect that we believe is going to be critical, much like what we ended up having on servers on Earth, that you started having these secure hardware as ability to offload certain very sensitive and high value compute to different parts of the processors or the onboard computers in the case of space, right? Like you have on every spacecraft an onboard computer that essentially we'll believe that we'll need to see SpaceFabric architecture embedded into every space system in order to give you these security guarantees. that I guess like just touches on the direction that we're taking it in terms of commercial deployment, but cannot discuss yet the specifics of partners and applications that we're working with on pipeline.
Is the security sufficient today for a data center today? Or is there a timeline, in your opinion and in your guys' perspective, that is needed to establish a baseline for data center security that we don't have yet? And the reason I ask that, I don't remember the name of the company, but John Jossi might step in. He has a better memory than I do. And we both got an email about a company that's launching and is taking orders and servicing people with data centers right now today. So is there sufficient security? I mean, I think it's a little premature, but John, you can correct me if I'm wrong. They were saying, come one, come all, we're ready right now today to give you your space data center. So do we have sufficient security for this today? And where are we in that timeline to have sufficient security if it's not there today? Anyone want to answer?
Maybe I can then try to chime in. So at least I think where we currently see it, the level of security is not there yet, so to speak. And I think it's not only about where we are currently at, but also where do we foresee the future of compute in space going as well. And as Daniel was mentioning, for example, AI is great in many things, but definitely currently what we see in general, not only with AI, but in general, is the aspect of observing fake information being circulated around. It's hard to determine if information is correct and authentic from the respective source, or if it was tempered along the way of the particular communication as a part of the supply chain and individual parties that actually are touching on the respective information and the data itself. And we see this is currently becoming a challenge with respect to where we currently operate. And I think the other part, which is very unique to space, which is the part where we also focus on, is to mitigate and solve the problems regarding scalability and provide the solutions to that. And I think the aspect of scalability that is currently causing limitations in space is also the aspect of trust and the results with respect to the sharing of the infrastructure. Because currently most of the payloads that are deployed are used for a single purpose by a single operator, and there is not as much of the shared infrastructure that we would like to see to, which I think is very important for the aspect of unlocking future use cases and lower the barrier to entry with respect to sharing infrastructure and making it also secure. So it's like I would say also a unique opportunity that we would like to see if we can build up the security ground up and unlocking for the future use cases. So to answer your question, David, at least as when looking at the current protocols, the current threat models, we don't see that the security is on the level that it should be, especially considering that the space infrastructure will be more and more open and will be more and more part of the critical infrastructure. So there is definitely quite some need for rehauling it and improving on the state of the art. And especially if you look at, for example, some of the recent studies based on, for example, academics research, they found out in a recent paper from roughly 2024 that around 50% of communication is being transmitted in space is not even being encrypted. So that way anyone who can listen can actually later on see the information that are being exchanged, which is of course not ideal for the consideration that is still a part of the critical infrastructure. The state is getting better, but of course with new openness and new parties joining the game, the security will also have to rise, but also hopefully can rise with new type of requirements that will be unique for the space as well.
John,
What sort of
David,
requirements are
David, to
there?
answer
Oh,
go
to
ahead,
answer your
John.
question,
Yeah,
to
go
answer your
ahead.
question, sorry, Phil, just real quick. The company that you were thinking of is called Atomic 6, and they were featured on Varney and Company last week. If you go to their website, it says orbital data centers are here. The wait is over. Orbit is ready for your compute. Spec a dedicated data center in space today. We handle everything else. So
So
I don't know
maybe
if you guys
just
are working. Are you guys working with Atomic 6, by the way? Just curious.
we're not, but would love to connect with them. So definitely thanks for the reference. But maybe just to give a gist on where currently the industry is, which I'm sure that that you guys will appreciate considering stuff that you've seen over the years that sometimes people that are newcomers forget. So first of all, the entire premise for space-based data centers is banking on the readily available access to Starship in production. Because when you're looking at actual data center scale compute deployment in orbit, it's not something that is a small rack of Raspberry Pi or even a single H100 NVIDIA. You're looking at quite a bit more beefy, performant rack. And this, I'd love to speak to Atomic 6 and everything, but like in realistically, from what we're aware of, the most advanced companies are not yet, including SpaceX, by the way, are not yet building the scale of data centers that we're familiar with from terrestrial solutions today. So these are all essentially banking on that. And coming back to the security questions of space today, so this also brings something very interesting that you are all probably familiar with the days where the concept and interpretation or prediction of where the internet will take us. There used to be the premise of AOL walled garden, where every dominant internet player in the late 90s, early 2000s thought that they will have some kind of a siloed internet version where they are able to feed customers with whatever is happening there. And this is more or less what you see today in space, where every space company is trying to service, including Starlink, by the way, right? Like much of what you have is like a single company that is trying to service customer base rather than looking at it as something that is very open, interoperable, and essentially work as the internet that we know and love today. And that's a big part of what we're trying to seed here as a major differentiator, because we believe that the way that the space internet will evolve will resemble a lot more this trend than having like a single company that owns a data center and services everybody with solutions. We'll see much more interconstellation communication, providers from different payload types that can essentially work together through protocols, and all that is going to require high degree of security, which essentially this is the core focus of what we're doing at SpaceComputer.
John Hunt had a question and is waiting patiently.
Yeah, I'm going to just try to understand what you're doing here. Is this basically working on a subsystem that will go on the other people's satellites to for communication security on them? Is that what this is? So you're looking to be like a subsystem to the other company's satellites?
Yeah, it's one of the part of the offering, and for that one, we are focusing on the hardware that can be, for example, integrated on the payload. We are also looking into integrating it on board of the onboard computers. And in case, of course, you're already having your solution in space, we also want to provide you the respective software libraries that can, for example, provide a security for the communication between the ground segment and space, and can also later on, for example, provide, as Daniel was mentioning at the beginning, provide you not only capabilities with current cryptographic primitives and algorithms, but also focus on post-quantum cryptographic security as well, which is something that, of course, if you consider the design lifetime of the satellites and how long it takes even before you design and send something to space, it's very important to start to take this type of threats from quantum computers seriously and have solutions and ideas regarding that already moving forward as of now.
So I was wondering, like you talked about security and implied that people weren't always encrypting stuff in space communications, but in terms of just the technology itself, like what kinds of technologies exist already for terrestrial communications, and why aren't those technologies sufficient for space-based communications?
So I think the technologies that exist on Earth, like algorithms that are already being discussed and used in our broad internet, I think they exist and they can be ported to space. Just people, I think, are not really doing it in large numbers. And I think this is the part that I think, same as we have started with the internet, and HTTP was the main de facto protocol, and HTTPS with the log appeared several years later. We, I think, are having a bit of a deja vu with respect to where the state of space security currently is. Where I think at the beginning people are thinking, oh, only state level attacker can maybe listen to my communication. Let's even focus on how do we send information to be able to listen to them. But now as it's becoming more commercial and more open, I think the new type of requirements are popping up and have to be considered as a part of the solution.
Mm-hmm. I was thinking along the lines of your blockchain security, which is probably about the best thing out there as far as I know. But there was a major problem with, I think it was called Bitcoin mining, where you had to produce the keys that were communicated back and forth. Are you doing anything in the developing a new system to produce enough keys to do a worldwide blockchain system?
Maybe to at least clarify my understanding of Bitcoin. So at least the mining in itself is to try to find a respective collision. For example, that I have certain number and I'm running it through an algorithm that is called hashing algorithm, which will later on end up with having certain number of leading zeros at the beginning. And this type of compute is quite expensive. But once you find it, you can actually just sign it with your respective private key, broadcast it to the network, and later on anyone is able to verify that this is actually an authentic message, because I'm also sharing the solution to the puzzle that I'm solving as a part of the proof of work, and I can use the current existing infrastructure for that already. So on that part, I think that if you would like to do mining in space, it will be, at least with the current technology, not as efficient. But also on the part which maybe our technology could be used and support these type of systems, it's, for example, providing them attestation or checkpointing that, okay, actually this is like the valid information. And it wasn't only verified in terrestrial system, but it's been also verified in the space system that is, for example, equipped by the SpaceFabric architecture we are talking about. So it can be maybe considered as a layered approach as a part of it. And if you will like look even one level deeper, what you would be needed to even do something like a distributed system as a type of blockchain in space, you would need, of course, like a larger constellation that has compute capabilities on board and allows other peers to communicate and exchange messages in a more seamless fashion, because these type of systems are very much communication heavy as well, in addition to, for example, to the proof of work solution that is also very computationally expensive as well. So we are looking into some ideas more coming from the aspect of what are the properties such protocols provide, which mainly is synchronization in the context of that all of the parties that are involved in this protocol have the identical state of the system, which is very crucial for some application where the state, for example, can be a ledger, that all of us agree that the payment between, for example, me and Daniela and me and David is identical, and I cannot be telling that, hey, I have 1,000 euros and I sent 1,000 to Daniela, but later also want to send this information to David later on. Basically, this is kind of enforced by the state synchronization provided by this property of the system, but we try to rather focus on what already can be unlocked by a single satellite, and later on be scaling it to a larger scale system as well.
It's still going to be very computational heavy, and it's just one of the prices you have to pay for security.
Correct. Yeah, I think in that sense, the security will be adding additional overhead, but at least with the technology that is called trusted execution environments, the overhead on the compute is not so prominent, and we actually see that it can be roughly on par with the regular computer services that we have available on the spacecraft. So we are trying to choose, I would say, rather secure, but a reasonable secure solution that doesn't introduce so much overhead, because, of course, the dilemma between security and usability is something that we take very seriously, because we want to ensure that the security is also coming with usability to improve and provide the adoption to the users as well.
Do you have competition, and who are your competitors?
Great question. I think on that part that when we look into the details, some of the competitors are, for example, looking into some of the software-based solutions. But I think what is quite unique is from our side is the combination of the hardware and the software together.
When you're doing the design, how are you looking to mitigate the radiation and the thermal effects, and how are you looking to ensure that once they're in space, they're actually going to perform as expected? I guess ground-based space environment testing, that kind of thing. Can you describe that?
It's a great question because especially with cryptography and radiation, these two things are not the best friends of each other, so to speak, because cryptographic keys are very sensitive to any type of bit flips. Because of course, if I have a 32 byte key and something goes wrong with it, it can result that I won't be even able to decrypt the information that I'm receiving from some other party. And on that part, we try to do it in a layered approach by having hardware that is, of course, properly shielded to provide radiation protection. We of course have also similar means to ensure also thermal heat dissemination of the heat with respect to that. So it's like usually a mixture of aluminum that we are currently looking into to have like really sufficient layer of that. And what we also try to do later on is on the additional aspect of the hardware, which is mean that we are also having redundant compute units on board of the same hardware payload we are designing. So we are not only relying on a single compute, but we have actually multiple of the same type of compute units themselves to ensure redundancy with respect to this type of computation. And then we can actually do also quite a few aspects in the software. So we are regularly, for example, checking that our keys have been not tampered with. And also some of the hardware components we are using, they have inside of the chips, they have dedicated alarm units, which in case there will be a bit flip, we basically get a notification that this has really happened. So we will try to take a structured approach on how can we enable sophisticated cryptographic operations in space without worrying, or it will be never worry-free, right? But it will be at least try to minimize the likelihood that something will go wrong with respect to the private key status. That is very the fundamental, let's say, unit we are speaking with respect to supporting users and provide the means that we are looking into.
And how about the space environment testing? Have you been doing that in advance?
Yeah, so on that part, we are going through various stages. So we either try to simulate some of the properties. We also try to understand in the labs properties with respect to, for example, how many single site events the respective chip can handle before it starts to deteriorate in its behavior. And we also try to make sure that this type of information can fulfill the lifetime of the mission. So we have done some testing on that part, but of course, until we see it completely from space, we will actually not be able to tell if the lab information are matching the reality, which I think is, as Daniel was mentioning, it's a really important step for us to now go from the no heritage to heritage and basically see how does our design choices later on behave in space, especially considering this type of deeply technical cryptographic applications that we are looking into.
Do you see your technology being used kind of in the AI data center fabric, where the bandwidth and performance is super critical, or in like a space application, or would your technology just not run on that kind of high bandwidth fabric?
It's a great question. So there are varieties of the technology. So for now, we are not focusing on the large scale, let's say AI workloads that will be very demanding, like the type of LLM, but rather are focusing on a more smaller scale machine learning models that are more made for a particular purpose. And for those, I think we are in a good shape. So for example, if we consider, okay, I take an image or several images, I want to pre-process in space that only images that, for example, are not having any clouds on them. And I only send to the Earth users clean images without any type of visibility issues. Then this type of actual algorithms we are able to operate. If we talk about LLMs or any type of more expensive AI applications, we are not there yet with respect to the technology.
You're really thinking more like inference workloads or smaller is what you can do.
Yep.
Because you were talking about actually separating different tenants on a single satellite. I assume a single satellite is going to be smaller than a data center on Earth. So you're definitely talking about the smaller type stuff, not the training exercises or anything
Correct.
like that. Yeah. Okay.
Correct. But of course, we are also looking, so the technology of the trusted execution environments is something that other hardware manufacturers are working on, and we hope to get in touch with them basically along the way, like either types of NVIDIA, Intel, and others that actually can provide this type of technology, and we can work on them to basically provide the integration, make it space ready, and keep on developing the software stack on top of that. Because there is quite a few tweaks that have to be done and make it usable. So we're actually actively in touch with several hardware partners to make it more applicable to space as well.
One more thought I had was like on Earth, the latencies between different data centers or compute clusters are pretty much constant, like they don't move around. Whereas in space, your satellites are moving around a lot, and I would imagine you get variable latencies between different satellites that want to communicate with each other. Does that create an opportunity for some new technology to solve problems that don't need to be solved on Earth?
I think so. It's definitely what we are like. There is so many opportunities, and I think many of the use cases and how this type of design will unfold. It's very unique. So, for example, even if you look at data centers, they, for example, are using the whole row inside of it for maybe one single customer that has like direct memory access from one rack to another rack, and they have to communicate to each other. So even within the rack, there is a lot of communication. Across different racks, there is a lot of communication. But now, how do you do this type of solutions and design the protocols in space? And I think there is like so much interesting opportunities with respect to that that I think will be a lot of protocols, a lot of design choices, and a lot of software and hardware architectures to unfold along the way. And this some of the protocols actually that we are planning to work in the future will be trying to solve this type of use cases as well. How can I, for example, have my satellite that is waiting for a computer that is running on another satellite, and only when we see each other, we are able to synchronize the states in between them without actually me waiting and idling for the compute being available. So this is definitely something that is very interesting use case. For now, what we are rather focusing on is already the capabilities that we can do on a single satellite. So for example, in a rideshare scenario, you have multiple payloads, and you can consider that currently each of the payloads don't really nicely communicate with each other and don't share resources. So we're actually interested in looking at how can we share the resources, for example, between one more powerful payload and another less powerful payload on the same bus system without compromising on the security. So these are also some of the use cases that we are looking into and try to provide the solutions for them to be able to unlock more efficient architectures as a part of the story.
If you, as a private company, are working with other private companies with all of this high security, are you finding out that governments are finding out about it and saying they want in or access to your security? Or can your security be business to business and governments are stepped out of it?
You want to take that one, Daniel?
Yeah. So as you might know, in many places there's like a bit of a, don't know if to call it hierarchy, but there's sometimes certain things are more sensitive than others, and there's oftentimes a larger vendor that has relationship with governments that then goes and solicit solution architecture or vendor relationship downstream to procure specific solutions. So what we're seeing is that the people that or the organizations that are more deep in the weeds of integrating spacecrafts and ultimately sometimes servicing government with these solutions, they're the ones that have the resolution to really look into, oh, we understand that our security is somewhat outdated. We understand that we're not post-quantum ready. We understand that we're not going to be able to interoperate. We see that the timelines are really long. We need to partner with SpaceComputer and other organizations to look at going to market with new solutions that are more fast to actually implement than what the world used to be in the past. So I'm not sure if it answers your questions, but the rationale just there is that there's different beasts in the space economy, if you wish. They're all moving with very different time constants. But ultimately, anyone that understands how things work, government or private sector, understand that there's a lot of things that are going to have to shift and change with security and generally the internet stack for space.
Are you, as a company, highly dependent upon a Starship operational timeline, or can you weather their delays and their going operational is not such a big deal? And then what would post-quantum security look like? What are you talking about with post-quantum security as compared to what you're trying to build now?
Sure. So I'll take the first part of the question there. With regard to our dependency on the Starship availability, No, we're not, and that's a very conscious design choice that we've made. So essentially, we're not ourselves directly a data center company at this stage. It might be a nice endeavor to dabble into once we grow and get a constellation and all that stuff. But at this stage, we're intentionally designing architecture that is relatively lean in the sense that it can be deployed with either the Falcon missions or to the question that came earlier with Electron or otherwise, right? Like ultimately, we're looking at very interesting security features already with the existing launch modalities that are available today. Now, obviously, like launching anything into orbit is something that takes long timeline. I know that Elon is talking about launching with Starship. Some of the predictions are 2027 already. I did a back of the envelope calculation of what does a 1 million satellite look like with a very conservative satellite form factor of, let's say, 100 kilogram. And I concluded that what we're going to need to see is a 1 or 2 Starships per day for about a full 3 years to reach that. So I don't think it would be the wisest thing for us to bank on Starship availability as much as I'm very excited about it. And we're definitely looking at the future where we'll be spacefaring civilization, all that stuff. At the moment, we need to be, with our heads in the beyond the clouds in space and our feet here on our beloved pale blue dot here. So we're definitely thinking about a lot of applications that are very relevant for today and are very possible to do today. And still at the same time with the outlook of how does that maintain forward compatibility with the security that will be needed in the future that data centers are available, Starship is available, as well as quantum computers are available. And this is where essentially the designing for it to be future compatible is really critical. And for that, I'll hand it to Filip to describe what we're actually doing there.
So with respect to the post-quantum security, I think the main aspect where quantum computing is very prominent for us is the assumptions we have on the underlying public key cryptography algorithms. So if you consider public key cryptography, it usually assumes you have a private key that is owned by you, it's selectively private, and you have a public key. And anyone who has the public key is able to verify, for example, that a message is coming from you. And if you look under the hood of these algorithms, they rely either on assumptions that are related to discrete logarithm problem or factorization of large numbers. And unfortunately, there are a couple of algorithms in the quantum world that enable very efficient means on how to solve these problems. For example, for the factorization of large number, there is the Shor's algorithm that is very efficient in solving it. And this basically means that the underlying assumptions of the public key cryptography will no longer hold. And because of that, we are looking into the world which will be after the quantum computer is there, it's enough powerful and can break the current cryptography, will provide the post-quantum cryptography security means. And the general idea is it will be relying on very different math under the hood, which is currently not as developed, it's quite fresh, but the algorithm that can be used will function in a similar fashion. You will have a private key and a public key, but to solve the problem, the underlying hard problem, will be also not difficult only on a classical computer as we see now, but will be also challenging on the quantum computer once it's gonna be around. And for that, the important use cases where public key cryptography is available around us, it's either relying on signing. So for example, as I was mentioning, I want to send a message that is really coming and it's bound to my respective private key, and I want everyone to be able to easily verify it. But it's also very prominent for the use case when I want to be establishing a secure communication channel between me and Daniel, for example, and only us, the parties that are actually part of this initial handshake, will be able to actually go and later on have the secure communication in place. The challenge coming with quantum computers has been known for some time, and this is the motivation also why, for example, the NIST standardization organization in the US is already started a competition to provide set of standardized algorithms that can provide you the post-quantum cryptographic security. And already a couple of algorithms made it to the finals, and they have been selected and are now being more and more adopted by the industry as well. And we are trying to be the pioneers with bringing the post-quantum cryptographic security also to space, and are implementing these algorithms on board of our software libraries, and also looking into the integration into the hardware to provide additional security capabilities as well. This is something that is, I think, very exciting. It comes with additional trade-offs with respect to the communication overhead, but also to the computation overhead. But it's definitely something that is crucial for the systems, because to give some timelines into perspective, for example, by the year of 2029, Google will be shifting all of their infrastructure to be post-quantum cryptography ready, because they believe that the timeline when the quantum computers will be enough powerful to break some of the underlying assumptions of current algorithms might be around rather soon after. And it might take, of course, time to migrate so many compute systems that we see around us in a fast pace, in case the quantum computer will be around. And they're already taking precautions to make sure that the infrastructure can operate moving forward as well.
Jossie, you have a question?
Well, I took my hand down because he sort of answered it. I was going to ask, what is the current forecast for when we can expect quantum computing? But it's hard to do on the ground. I mean, you need these, you need superconducting, cooling with helium, and is that really going to be on orbit soon?
I don't think so. I mean, I hope it will be around, because it's a super cool technology, right? But I think it's gonna take some time before we get there, at least from the current perspective. I think a little bit feels like it's like with the fusion. How far ever are we from the fusion reactors? 10 years, for the past 50 years, or how long? So I think there are two different camps with respect to the quantum computers and how fast they'll be around and how performant they'll be, how many qubits will they have. But of course, with respect to security, at least on the mathematics side and cryptography side, it's better to play it safe with respect to having solutions in place, which might not end up being relevant unless there will be really enough powerful quantum computer. Then to later on, once maybe a major breakthrough happens and you really suddenly end up having powerful enough quantum computer that can really damage and basically change the way on how security is currently handled on Earth. So I think it's better to be a bit more cautious with respect to implementing the solution and be ready for the quantum day, so to speak.
I have another question for you. Many of us in the room, but some of us who are not here, live in an area in the United States where the thought of putting an orbital data center in your neighborhood, or probably within a zillion miles of your neighborhood, is absolutely unacceptable. One of our members who could not be with us today says every place he goes in Maryland, he sees no orbital data center here. I'm curious is if you are experiencing not no orbital data center, no terrestrial data center here. Are you experiencing where you are in Germany and Australia, neighborhood civilian resistance to data centers being built in your areas?
It's a very polarizing topic, because I know that some countries would look at it as a fantastic opportunity to get on the wave of AI and become a part of it. And some, as you alluded, there's the NIMBYism, right? Not in my backyard. There's NIMBYism maxi at this stage, and that's a big part of the push for orbital data centers. So, I mean, I know in Australia that there's going to be a lot of AI data centers here. And naturally, it's typically the bandwagon topic of the day to be against, for that people are jumping on. Oh, I hate data centers today, just as I hate some other, insert some cause du jour to be against for. So I think that it's fine. Like it's probably it has some merit in some cases, but for the most part, it's just some like sentiment that people have. As an NIMBYism sentiment, I see. Yeah.
What about Germany? Are you finding it there too?
I think that it's being heavily discussed for the various reasons. Of course, one part is the continuous noise coming with it, but I think especially over the past years, there is a lot of discussion regarding the amount of water some of the data centers need. And of course, depending on the neighborhoods, some people are more for it and some people are more against it. So I would say there is definitely more of a questioning to try to do it responsibly. But of course, this is not ideal because it can take extended period of time, and it's also like a matter of staying competitive. So I think there is a lot of discussion about how it can be done correctly, but hopefully it will not kind of deter a lot of the progress that has to be made. But at least it's a polarizing topic here as well.
AJ, you have a comment?
Yeah, I have, I guess, kind of a question. A while ago, I guess a couple of months ago, you may have seen Carlos Garcia Galan of NASA talking about phase 1, phase 2, etc. of lunar exploration. And there is also a lot of effort going on, or some effort going on, that was started by J.J. Miller of NASA, was on PNT, which is positioning, navigation, timing. Is your technology useful for that? I mean, especially if there is going to be a need for some kind of classified secret or some kind of proprietary transmission back and forth, especially because of China and United States both trying to set up settlements there, etc. So, do you think that there is some play, or I mean, the other way to ask this question is: have you been thinking about applying this technology on the moon settlements?
I think the technology itself should definitely be applicable to this type of systems as well, especially if you consider that I'm sending sensitive information and I want to make sure that the data that are being transmitted are secured along the way. They are maybe having integrity protection and other means of security in place. And this can be, if we don't even consider moon settlements, but even look into current on Earth systems, for example, like GPS, there has been a lot of issues with respect to jamming or spoofing messages along the way that were later on tampered with in the transmission, and maybe try to later on provide incorrect information to the receiving side. Our solution can definitely help with some aspect of making sure that the messages cannot be tampered with in the transition. So, of course, in case there'll be challenge environment on the moon settlements as well, it could be something that could be applicable for this type of scenarios as well. So that way you don't have to worry about the message being spoofed, but you really want to make sure that that you have the cryptographic means to ensure the integrity and the availability of the message, maybe by different means as well. But this is something that we don't provide is, for example, something like jamming protection, because this is definitely something that we are still relying on the physical communication layer, both RF or optical. And in case the signal itself will be so noisily, so to speak, jammed, basically our solution will not help, because just the channel, just the communication will not be even able to go through. But if you consider the messages are going through, you just want to make sure that they are integrity protected. Our solution could help it.
I have one more question, I guess, for Australia, basically. So perhaps Daniel can pick that up. There is a lot of, I mean, I've been watching and listening to all these things, and there's a lot of opposition to nuclear power in Australia. I think still, probably also in Germany, of course, obviously. They shut down several plants, and I think it's kind of changing a little bit. But for terrestrial data centers that we discussed a little while ago, one of the solutions being offered is nuclear power, and within nuclear power, advanced reactor nuclear power. Are things changing in Australia about nuclear power at all? This is a question for Daniel, and I guess maybe for Germany also.
Yeah, so I think this goes back to the same discussion about the NIMBYism. It's very interesting that you see a bit of a polarity between people that are very interested in seeing advancement in technology, energy production, nuclear, and then you see often also just resistance to anything that is new and innovative and stuff. So you kind of have both voices. I know that in Australia, generally, there's actually quite good reception to these things. So there is definitely interest, and I know, for example, the Australian military has changed the contracts from getting the submarines from France to getting the American submarines with the nuclear generation ability. So Australia is actually quite inclined to be pro-innovation overall. I think maybe the sentiment you pick up, New Zealand is a bit more conservative when it comes to nuclear energy. There's like quite a lot more greenies and the general resistance to this kind of things that are perceived as, oh, that's like too modern, too like polluting and stuff like this, without even like going to the nuance. So I think this like how it's like it's just at the resolution of where I'm sitting from. And yeah, Philip, maybe share the sentiment. I know that Germany obviously had like a pretty big change in after
Right.
the Japan
Fukushima.
disaster. At
Yeah.
the time, I remember there was like a big policy change. So
Yeah, I think it's a little bit now coming back in the sense like there is not sometimes enough energy for maybe the future supply for compute. So I think at least for the current sentiment is actually people are not very happy with respect that there is no nuclear energy around. But of course, currently starting or even going and reopening the existing plants is very challenging from a technological perspective. And even if there'll be new motivation to build new reactors, it's gonna take usually decades before such reactors are built. So I think there is a discussion a lot about what can be done regarding other alternative sources of energy. So I think, of course, solar wind is becoming very popular. Hydro nowadays is a little bit less stable. Maybe I'm not sure if you have seen it, but there is a huge amount of droughts currently going on through whole Europe. So there is a lot of discussion actually regarding hydro, at least in some areas, being heavily discussed. And maybe actually on that part, definitely solar seems to be picking up. But of course, they are also considering maybe some nuclear reactors to be either reopened or maybe consider a massive project for the future. But it will not solve the demand issues now because it will maybe take 10 years, even before it's being fully constructed in an optimistic sense, right? As we see with this massive type of projects, it can sometimes take between 15 to 20 years and has massive delays, and the price tag increase, you know how many folds. So there is a lot of discussion on how to solve it. But I think at least the good part, there is a discussion and people are realizing that more power will be needed for the future infrastructure that is relevant and will be heavily reliant on compute capabilities.
I have a question about like how far into the future are you guys thinking? So, TCP/IP, for example, was invented early in the early days of the internet, and it's still being used today. There's IPv4 for internet addresses, and that's been replaced with IPv6, which is only just been needed recently. But as you think about expanding into space and potentially, one day will be a Dyson swarm of compute or something like that, like huge, maybe galactic level internet will one day occur. Are you guys thinking that really long term in terms of designing and architecting your solutions so they will never run into limits in the future that force a massive redesign of the entire infrastructure?
Optimistically, we definitely try to, but there is of course a lot of stuff that we might struggle to consider. But at least as a part of the motivation and aspiration, this is definitely the target, and we see it, at least from my perspective. I see it as a unique opportunity to see how we can contribute with maybe different type of requirements and understanding, and see how we can build up the new infrastructure that is currently being expanded, shifting more and more to space, and see if we can provide some unique contributions in that direction, which is, I think, really a unique opportunity on that side. Let's see how many of these ideas and contributions will be picked up. But at least if you can play a small role in this, it will be definitely something interesting.
Yeah. I think this is like also a bit of a your question like touches on both very pragmatic things on design choices that you make today, but ultimately I think that it's always nice to remember that as civilization, there's I'm sure you guys are familiar with the Kardashev scale. So if we're working towards getting like realizing Kardashev type 1, you always want to look at what's beyond that and start thinking about Kardashev type 2. And when you're looking at Kardashev type 2, the space systems that we're building today hopefully will be powerful enough to be the substrate on which autonomous AI systems that are spacefaring on their own are already able to develop future compatible space internet stacks. So hopefully the architecture and the design choices and the discussion and the aspirations will be enough of a data set for the future Kardashev Type 2 models to learn from and be inspired for so that we can see them building it themselves as autonomous agents aboard different manufacturing bases in Moon and in Mars and beyond. So it's really like hard to know what will the future look like, but we can only hope that we're a part of a um, light cone of consciousness and building at the ultimately the infinite frontier that is space. So I think this is like a big part of what brings us probably all together to this show, right? Like I think we're all a bit of a space nerds that are happy to tinker and do our part in the humanity's light cone consciousness projecting into the future.
We're at our 90-minute point, which Philip mentioned was a good point for you guys. Have we forgotten to ask you something, or do you have any concluding marks or anything that you want to say? And the same for any of the space show people, just keep it concise. But it's been great having you on the show, learning about SpaceComputer and what you're doing. And we'd like to follow and touch base with you later on and see how things are going. But I think it's been a great discussion, very informative. But if anyone has a concluding comment, speak up now. I guess no one has a concluding comment. Anything else from Daniel, you, or from Philip, or Max? You're still with us, I think. Anything that you think we should have talked about? Silence.
I think we covered it all. It was definitely great to be here, and thanks a lot for the wonderful discussions. Maybe a short comment. We'll be in the US, traveling from all our corners of the world during the Silicon Valley Space Week, and if you happen to be around, we'll be definitely happy to meet you in person. Thanks a lot for having us.
Okay, well, our pleasure, and hopefully you'll be amenable to come back on, and we'll see how you're doing. And we thank you very much for being here. Everybody have a great rest of the weekend. Although for Philip and for Daniel, the weekend's long over with. So, but still here in the West Coast. So thank you again, everybody. As we like to say, keep looking up, and don't miss our other spatial programs coming up this week. And goodbye from Marshall, John, Bill, Philip, John, and AJ, and myself. Thank you again. And Max, thank you again for your patience in getting this put together. Goodbye, everybody.